Hello everyone, welcome to Learn Overflow. In this video, we'll discuss to this LeetCode problem, that is the reordering power of 2. This is a medium level problem and we'll understand how we can think of finding a solution to this kind of question. We'll see much more examples than this two and we'll understand this step by step. So first of all, let's understand what the question says. The question says we are given an integer n, so that's the integer n given to us, and we need to reorder the digits in any order, including the original order, such that the leading digit is not zero. Okay, so we need to reorder the digits and such that the leading zero should not be the leading digit should not be zero. So that's the idea. Now, whenever we come across something like this, so that basically means we need to do some permutation. That's a normal idea you should understand out of it. Like you should, when it says like reorder the digit, it means you are just permutating the various combinations and like various permutation of the digits and you're just changing the order. Okay, so that's the basic idea they want to give you over here. Now, further it says like return true if and only if we can do this so that the resulting number is a power of 2. So we need to check if the resulting number after the particular combination is a power of 2 or not. So what it exactly means, like say there's n equal to one, like if it's one, we know that power of 2 to the power 0 is 1, so that's by default it's true. Okay, so if n is 10, can we change it in any order and find out that it's the power of 2? See, the other combination, like other combination of this will be 0 1, fine. One is 1 0, the other one is 0 1. You cannot do any further combinations to this. So if the other combination is 0 1 and it says like the leading digit is not 0, so this is not a valid combination, valid permutation we have. So in that case, 1 0 is the only permutation, and we find that 10 is not a power of 2, like the resulting number is not a power of 2. Fine. So let's say we have something like 46. Okay. So if we have something like 46, is 46 a power of 2? No. But what if we change and reorder this 46? If we reorder 46, we can come up to 64. Okay. We just reorder that different permutation of this. So we find that okay, once we reorder this is a like power of 2 is there. Fine. So that's a like permutation we find. So if once you are given 46, you should know that this is the power of 2. So that's the idea behind this question. Say you are given a number like 24. Okay, say you are given a number 24. Is 24 a power of 2? No. Is its next combination, that is the 42, is it a power of 2? No. And we find that no, none of the combinations we can come up to, or none of the ordering of the digits we come make it to, none of this make up to like our desired result. The result that is a power of 2 or no. It's not possible. Okay, so that's the idea over here. So further, if you look at the constraints, in the constraint you can say our n will vary from 1 till 10 to the power 9. If we are varying our n from 1 till 10 to the power 9, then how many power of 2s are actually possible? Because if you keep finding the combination, like permutation of each of the digit, and our n is something like a huge number, like a 10 to the power 9, like there are like 9 digit number, fine. That's a huge number, 10 will be, right? So if it becomes that big, can we keep on doing this permutation and find out whether anything is the power of 2 or not? Obviously not possible. Like that's not a feasible solution within our given range. Like we are not a feasible solution thinking of our like the complexity of the solution we were trying to do. Like we may end up finding a solution, but that won't give us a much faster result, or not the good kind of solution we can find out. So we need to think of finding something better. So what we can do in this case, we can see that we have a number like 10 to the power n, and if we count the all the like numbers that are like if we count the all the number of digits that are given, say in the number like 2 is given 3 times. Okay, so if 2 is given 3 times, say in different places, fine. And the further we find like 3 is given 2 times, 3 is given like 3 is given. Okay, and we find 1 is given 2 times, like this is say this is a number given to us, n given to us, fine. That is valid because it is less than or equal to 10 to the power 9, right? And this may happen. So if this kind of a number is given to us, the idea will be to like count the number of digits in the given number. Say we'll find something like that, like if 1 is there, we'll find in this manner. Say we can use an array for this, for something like we use an array of all the 9 numbers, and then in that we'll store like this is 0 position, we'll count the number of zeros. Number of 0 is 0. So this is the position 1, so we'll count the number of 1. 1 is 2 times 2, 2 ones are there. Further, we'll count the number of 2. 2 is like 3 twos are there, right? Then it's the number of 3, and it's like 2 threes are there, and further, all those are 0. Now, the first we can do something like we can have a count of this, because whatever be a combination we go up to, like whatever be a change we go up to, our number of digits will be fixed, right? Our count of the digits won't change anyway. We just need to switch their positions, right? Now, once we do this kind of count, and then what we need to do, we need to check for like the power of 2's that having the same like same count. Okay, if we find any power of 2, say we find say this let's take this example, okay, 64. Now we're given 4 and 6. We find in our array, however we're storing, we find that there are 1 4 and 1 6. Okay, and then what we'll do, like that's the first count, we just counted it in one go. Next, we will keep checking for each of the power of 2 that is less than 10 to the power 9, because for each of the power of 2 that is less than 10 to the power 9, we actually don't have a large number of power of 2. Why is it so? If you look carefully, it will be more or less like 10, like power of 2 will be like 31 or 32 power of 2s will be there, not more than that. Like to be exact, 31 power of 2 should be there. Okay, that is less than 10 to the power 9. So in that case, what may be a good solution is like you keep for those 31 or 31 values, like to be exact 0 to 31, so it's like 32 values. So you keep checking for this 32 values, and in the 32 values, if you find somewhere that any of the power of 2 has 1 6 and 1 4, okay, because our initial count has 1 6 and 1 4 in our n, and if we keep checking for all those numbers and we find that it has 1 6 and 1 4, any of the combination of the power of 2, that means we can do that, right? We are not supposed to find the exact combination, but we need to check whether we can do or not do. Okay, so that means once we find that the number of digits, like the exact number of digits in our power of 2 and in our given n are having the same number of all the digits, that means we found our answer. Okay, so that's the whole idea behind this. Fine. So quickly, I will go ahead and write a code for this. The first code we'll find we'll use a different function over here. Find a different function over here. This function will be a counter function. I mean the counter function that will help us to count the number of digits of each of the first of all count the number of digits of n, and then keep on counting the number of digits of power of 2 that we come across. Okay, so we can do that. So now further we will not use an array over this place, because in that case we need to check for arrays dot equals whether two arrays are equal or not. Like that's a huge combination. Rather than that, what if we do something like we store it in terms of a long-term value. Okay, like a long value. What I mean is, say we have a number. Say we have a number like 20, like 232. Fine. I'm not checking it's a power of 2 or not. I'm just trying to show you how we'll store the number in a long-term value. First of all, we come across like we'll break this number at the last digit. Okay, we find this number that is 2. Now we'll do 10 to the power 2 will be 100, right? So we'll do 1 0 0. That will be our value as a long value. Say we just find our result value. Okay, result is 100. Next we divide this number by 10, and we are left with only 23. Next we, in the 23, we find a remainder of 10, that is the last digit will come out, and here we will find 10 to the power 3 in the last digit. So that will be like 1 0 0 0, and we'll sum of this like 1 1 0 0. That will be our result value after the second digit. Right? Look, what exactly is going on, I will tell you why we are doing this. Further, what will happen? We'll divide this by 10, 23, and we will be left with one digit. So in that digit, we again do like 10 to the power the digit that is a 2. So we'll do 1 0 0 that is being added. So the final result of our long value will be 1 2 0 0. Fine. Now, what will be the idea? Like we are not using a string, not using a array over here, but look, this is the 0th position in terms of maths. Think of it. This is the 0th position. This is the 10th position. This is the 100th position. This is the 1000th position, like that. But look here, this is the first position. This is the second position, and this is the third position, right? So that's how we do in math. So in different, like in a just in a conceptual manner, we now know that For 3, there's 1 3. That's in the third question. In for 2, there's two twos in our given question number. Okay, that's in the second question. Fine. For 1, like there is no 1, there's no 0, and other way, the as is a long value, so other values will be 0 as well. So that's the whole idea. So we are not using a array because array will take a large space. And instead of that, let's use a simple long value, and we'll keep checking that a number, like we don't need to use arrays dot equal, which will be like checking for each of the positions. Rather than we'll simply use double equal sign, which will be like two numbers we are checking for equality. So that will work at least for us. So that will be our idea of it. Okay. So let's first go ahead and write our counter function, which will help us in counting the values, and then we'll write a loop, which loop within this reorder power of 2, and that our loop will help us to check whether any of the power of 2 becomes equals to or n or not. So that's the idea behind this. Okay, so let's go ahead with that. So here you can see, like when we are giving 46, it's finding true that 64 can be a combination, and it was expected also true. So that's the case we find. Fine. Now let's submit this, and in the submission, I hope this will take a faster result. Yes, it's a 1 second solution, and you can see it's like faster than 100% solution is there. Fine. So that's more or less our idea behind this. Now, if we just try to understand what exactly we did in that, we simply first of all we did a counter. Counter is like, you see, it's a long time variable. Fine. As a result 0. So this will be the final result. So what we are doing for each of the, like while n greater than 0, like for each of the digits of n, we are just doing 10 to the power that digit, and in mod 10 will return as the last digit of it, right? So we keep on doing that, and the power actually returns as a double type value method power. So what we did like did a int of that. So once we did an int of that, so that will just erase off all the decimal numbers we come across. Even though it's like 00, even it is like 0.00, it doesn't matter. It will just erase them off. And then we're adding that to our long type. So we're just converting it again to a long. So it won't matter much. Just in case of any kind of precision error happens because of that method power, in case it returns as a like 0.01 or something like a error in that. So that will be just omitted for our case, which normally won't. Okay. And next we just did our n by 10. So we're just erasing of the last digit. Okay. We just made a like power to the power last digit, and we then erase of the last digit. So that's what we keep on doing. So that's how we actually extract each of the digit out of a given number. Okay. So as a normal process, and ultimately we just return the result of that. Now, what we're left with further is like we now in our main function we got our like the exact long counter. Okay, the counted value. What is the counted value? And then what we did, we just went ahead from 0 till 32. Okay, not 32. Like till 31, because 0 to 31 we'll check. That's what comes below this 10 to the 9. Fine. So if we're checking for 0 to 31, and in that, what we'll find if a counter, okay, count of this power of 2. If you don't know this, I will explain it in a moment. But if the count of our power of 2 is equals to our C being the character, like the counter of n we find, then return true. And after the whole loop, if we don't find anything return true, we'll return false. Fine. And if you don't know this I less than 1 less than I, so it is something like it works in this manner. So initially I is 0, so it's like 1 less than 0, right? So that's what we find across, and 1 less than 0 is like gives us 1 itself in binary. Then once you say 1 less than 1, so that means it left shift our digit, so it will be like 1 0. So initially it's like 0 0 0, some amount of 0 like in the way, and then 1, and then it left shifts that right one bit, and it's like 0 0 1, something like that. So this is equals to 2, this is equals to 1. Okay, and then if we do again 1 left shift 2, that means we left shift 1 2 times, so that will be like 0 0 not 0 0 1 0 0. Okay, so this is what, this is 4 in binary. This is 4 in binary, fine. So that's what we come across. If we keep on doing that, so we keep on doing this up to 32. So if we keep on doing that, so it will be like 1 less than 3. So that will be 16. So that is 1 0 0 0. that is nothing but 16 in binary. Fine. So this way it will keep on going. So what comes up as our complexity? Okay, what comes up as our complexity? Because see, what we're doing is like we are like in each of the case we need to understand what we are doing here. Fine. This is a kind of we are checking for each of the numbers. So what are the exact number of this? This is like n going ahead over here. Fine. So if this n is going ahead over here, so that means more or less 2 times it's running. It's a constant run. But the completion like the problem is not there. Problem comes up when it goes into the counter. The counter is actually counting for each of the digits. So counting for each of the digits goes ahead with the login time. So it's like once I log in for this and another login for each of those numbers. Like each of the like 32 numbers will do that. Like there's a login for different kinds of power 2, and each of the comparison has a login time complexity, right? So that's how it's like log in whole square or login square, something like that comes up. So it's much faster, as you can see. You already saw it comes up in a 1 millisecond solution, and it's faster than 100%. Okay, so that's the idea. So that's how it works over here, and it checks for that number and ultimately returns us true if it's true, or it returns as a false if we don't find any of the solutions over here. So that's the whole idea behind this, guys. So I hope I can make you understand this exact question we are given over here. And if you have any doubt till now, make sure to comment them down in the comments below. I'll be happy to help you out. Also subscribe to Overflow for regular LeetCode videos like this. Thank you all for watching this video. Hope to see you soon in my next video as well. Thank you.